Hello, everyone. For this lecture, we're going to be talking about the superposition principle, which gives us another way to calculate expectation values for our system. In other words, another way to represent a measurement of the physical properties of a system. So we already talked about the integral method for calculating an expectation value or an expected average value for a quantum mechanical system. So we used the integral method. We also used the eigenfunction eigenvalue method, which is a special case. It's not a general case, but it's an important enough case that it was worthwhile to discuss it. It's also related to the present case, which is where we use the superposition principle to calculate an expected average value. This superposition principle, it's one more tool in our toolbox that we're adding before we move on to actually solving the Schrodinger equation for some specific systems related to atoms and molecules. Okay, and it turns out also this superposition principle is, it sort of starts to neatly show some aspects of quantum mechanical systems in that you can sometimes think of a quantum mechanical system as being in two or more states simultaneously. And of course, this is something that's very much at odds with our understanding of sort of conventional physics, classical physics, where a system is in only one particular state at a given time. And it's one of the strange aspects of quantum mechanics and is related to some of the issues that we'll run across in trying to measure quantum mechanical systems, measure their properties, or perform various actions on quantum mechanical systems. And so this is somewhat related to something that you may have heard of, this Schrodinger's cat. Where the cat is in some superposition of states that's, say, alive or dead, depending on the probability associated with some quantum mechanical process. And I'm not going to go into any more detail on that. You can certainly look it up if you're interested in Schrodinger's cat. It's one of the quantum mechanical paradoxes. Okay, so the superposition principle, we have to just sort of lay it out mathematically here. And if we have a system in a state of interest, we'll call it phi here. And that phi is a wave function. Okay, so it's not an angle, it's just another symbol for a function like psi. There's nothing magical about psi. That's sort of your typical symbol that we use for wave function, but of course sometimes we need to talk about more than one, so or two different sets of wave functions, and so we'll maybe call another one phi. Anyway, so we have our state of interest, our molecule, our system, or whatever is described by this wave function phi, and we want to know an expectation value of some operator A. And so we want to know the expected average associated with the measurement that's represented mathematically as this operator A. Okay, and let's further suppose that we have a separate complete set of orthonormal wave functions, psi1, psi2, psi3, and so on, that I show there, such that those are eigenfunctions of our operator. So phi is probably not an eigenfunction of our operator, but we chose a different set of wave functions that are eigenfunctions of the operator. And we'll just give them some index, psi1, psi2, psi3, and so on, representing different orthonormal. So these are different state wave functions. They represent different states of a system. Might not even necessarily be states of the system that we're studying. They could be states of a completely different physical system, but that has that at least shares a coordinate system with our system of interest. And these are eigenfunctions of the operator A, such that acting our operator A on psi1 gives you the eigenvalue A sub 1 psi 1, and that the operator A acting on capital A, with a hat, acting on psi2 gives you a different eigenvalue A2 times psi2, and so on. In fact, it can be shown that if these are different eigenvalues, if A1 is not equal to A2 and so on, then by definition, or by, it can be proven that the individual wave functions are orthogonal. And we furthermore stipulate that these have to be a complete set, although superposition principle can also be used as an approximation method for an incomplete set, for say maybe a few of the largest terms. Okay, so then we've sort of set up the problem. So then we're trying to find an expectation value for some operator A for some system in a state phi. We have a different state. So we've sort of solved Schrodinger's equation, or come up with quantum mechanical solutions to a system, to a perhaps unrelated system or a simpler system, where we have a set of wave functions psi1, psi2, psi3, and so on. And these are eigenfunctions of this particular operator, and they form a complete, we won't worry too much about what it means to be complete, but at least a large set of orthonormal wave functions. And so, anyways, if we have this set up, then we can express our wave function of our system phi as a linear combination of this complete orthonormal set psi sub n, psi1, psi2, so on through psi sub n. And so it can be a linear combination, meaning it's a sum, that phi is equal to some sum over some index n, or it could be index I, whichever index label you want to use, c sub n, where the c sub n are our linear coefficients, and multiplied by the individual wave function psi sub n. And so if we think about this, this is a little bit like, say, the Fourier transform, where you take some arbitrary function and represent it as a sum of sines and or cosines functions. And that's been proven. And in fact, you can use sines and cosines as your set of orthonormal wave functions, psi1, psi2, psi3, in some cases. You could also use maybe different exponentials. So there are a lot of possibilities, and of course we haven't seen that many wave functions yet, but we will shortly, over the next few lectures. Anyway, so if we can represent our wave function. We don't necessarily even know what the actual functional form is for that wave function. Right? It may not be a simple closed form, in which case we can represent it as a set of, as a sum of orthogonal wave functions times linear coefficients. And this is also, yeah, I said it was like a Fourier transform. It's also similar to, say, a Taylor series, where you have you're representing some function that doesn't have a simple closed form algebraic expression, something like an exponential or sines and cosines. You can't just write them as a simple polynomial in X. However, you can approximate them to arbitrary precision by writing them as a sum of functions containing powers of X. So that would be like a Taylor series or a Taylor-Maclaurin series. So this is similar to that, where we are representing our wave function that we may or may not have a simple closed form solution for as a sum over some other functions where we have these linear coefficients. And we can think of those linear coefficients as being roughly related to how similar your function of interest is to that particular basis function or orthogonal set of orthogonal function psi sub n. Okay, so that's not all. So not only do we have the Taylor series part, but then here's where we really start to use the superposition principle. This is one of the uses. There are other uses elsewhere, in particular when we don't have a simple closed form solution, closed form expression for a wave function. This might be our only way to solve the problem. And we'll talk about that when we get into approximation methods much later on in the course. However, for now, we can think of it as this is a way of calculating an expectation value. Expectation value, you remember, or expected average, is denoted using these angle brackets. And so the expectation value for operator A, and I'm putting in the subscript a phi here, saying this is for a system in a state represented by phi. Of course, we know that the typical expectation value is given by this integral, phi star a phi, this sort of operator sandwich, right? But it turns out that the superposition principle tells us there's another way of calculating the expectation value, and that I've put in the box here, which is that if we know all of those individual eigenvalues a sub n, and we know the linear coefficient c sub n, then the expectation value is given by the sum of the individual eigenvalues times the mod square of the linear coefficient, Cn star Cn, which can also be written using this kind of notation that is a sort of shorthand for Cn star Cn, or Cn times its complex conjugate, right? That's the modulus squared, which is guaranteed to be real. Okay, so now we have that gives us a third way of calculating expectation values. One way is the integral method. Another way is the eigenfunction eigenvalue method, but that's just a special case. It's not general. This is another general method, but we need these auxiliary functions, these psi sub n functions, to sort of help us out, and the corresponding linear coefficients. And not only does this give us a way to calculate averages, there's a few sort of additional comments I would like to make about this. One is, as I stated before, it's like a Fourier expansion, or Taylor series. we can get usable answers, or maybe approximate answers, but approximate in that we can include as many terms as we want to get closer and closer to the true solution. Often we can be lucky and maybe the first we can get away with only including a few or maybe one or two terms in this expansion, and that'll get us close enough to the right answer. But yeah, we can get usable answers for complex systems. So this means we're not sort of stuck with needing to come up with exact solutions to Schrodinger's equation for arbitrarily complex systems, because as it turns out, sometimes those closed form solutions don't exist. The other thing that's strange about this is, or that's interesting about this, is something that's a little strange, is this sort of dual wave state or multiple wave state. In that we can think about our system as being in some state phi, but at the same time it's also in this superposition of different states psi sub n, psi sub 1, psi sub 2, and so on. And not only that, but it's simultaneously in each of those states with some sort of probability that's associated with these linear coefficients. In fact, the probability is related to the linear coefficient squared. But it's the sort of quantum strangeness is manifest in that this is a true random probability, in that before we actually, say, perform a measurement on the system, we don't know which of these states it's in. Then when we perform the measurement, a single system will collapse into one of these states, and the probability that it collapses into one of those states when this measurement is performed is given by this probability that it collapses to a certain state psi sub n is given by Cn star Cn. So that would be the probability that a system in some initial state phi, when we perform our measurement, will actually collapse into one of these states. Psi sub n, it's given by this Cn star Cn. And so this sort of introduces, we're not going to spend a lot of time necessarily worrying about this right now, but this is something that we'll see manifest throughout the course. And it's certainly worth mentioning, if for no other reason, that it shows a clear departure from conventional physics. And that let's see, what else did I want to say? Oh yeah, we have our third way of calculating expected averages. So let's First of all, let's see if we can prove this. Okay, and this isn't a mathematics course. However, it's not a math-free course. And so there are going to be some proofs. And that said, I will often not go to extremes to make sure the proofs are rigorous. I want them to illustrate a concept and perhaps help us to come to get a better appreciation for sort of why these relationships are true. I don't like to have sort of magic formulas that you use that we have that sort of come from nowhere, right? They should be justified. And so that leads us to having proofs. The other thing I would say about a proof is that I will tend to emphasize a proof where it exercises some mathematical steps, some mathematical procedures. I hesitate to say tricks because nobody's, there's no deception going on here, but mathematical maneuvers, let's say, or procedures that get you to an answer, and that perhaps give us a better understanding or appreciation for what's going on. So unlike some say, unlike some of your previous courses where there's some math, there's a little bit of algebra, you plug numbers into an expression, maybe you need to do a little bit of rearrangement to get, x on one side and a bunch of stuff on the other side, and then you're done. The problems in this course are going to follow procedures that are a little bit more like the procedures that you deal with in proofs. There are still some plug and chug, a little bit of algebraic rearrangement type problems, and certainly there's going to be some algebra in this course. But also often there are other steps beyond just sort of plugging numbers into a formula or rearranging a formula. There's going to be, say, taking words like, say, find the average value for this observable quantity, then we turn that into a series of steps that one performs and some algebra, and we get to an answer. And so it's a little bit more like a proof, even though you're solving a problem, but it's a little bit more involved than your typical garden variety algebra problem that you might run into in Gen Chem or maybe even freshman physics. So let's, without further ado, let's go into our proof. So first we're going to start with our expression our typical expression for an expectation value, which is this integral. Okay, and then we replace the individual phi in these expressions with the sums. So then we're going to have an integral over a double sum, and it's going to look like this. We'll use index m because we're going to have, sorry, I'm going to use n for this one. So phi star, we're going to represent with this sum. It's going to have Cn star and psi n star. Then we're going to have our operator. and then we're going to have a second summation over a different index, m, and then this is going to be all inside an integral, so there has to be a d tau there. Okay, now we can imagine acting our wave function, acting our operator on each of the psi sub m's. And that's going to give you, when you act it onto each of those individual psi m's, you're going to get back an eigenvalue. And again, we'll work through some not so abstract problems where we actually do this, so that's where this kind of proof can be useful. And this is an integral over all space. Okay, so we're going to get all of that stuff on the left, and then we're going to replace our operator with, so we've got that integral, that sum, and then our second sum is going to have these individual eigenvalues in it, because we're taking that operator, acting it on the individual psi m, getting out the eigenvalues a sub m. So then that second sum is going to look like this, sum over m, a sub m, c sub m, psi sub m, in parentheses, d tau. Okay, then we're going to do a little bit of rearrangement. First of all, we're going to put the two sums together on the left. That's not going to cause any problems. So we've got integral sum over n, sum over m, and we have doing a little bit more rearrangement, a sub m, c sub n star, c sub m, and then, oh yeah, actually we're moving our integral inside, and I don't really have time to justify all this, but if you could look at this on a term-by-term basis, sort of expand out at least the first few terms of this summation and kind of collect terms, you'll see that this is allowed, that we can move that integral inside the summation. The integral is only really acting on these psi sub n star and psi sub m d tau. Okay, so now we've got the integral. We've got just a bunch of constants out front. These a sub m, which are individual eigenvalues, those are constants. C sub n star, that's a constant. C sub m, that's a constant. And then we have this double sum. And then we have this, this integral, which we have seen before. This integral is the definition of our Kronecker delta, delta sub nm. And you may recall that, so these are an orthonormal set, and so this integral is going to evaluate to 1 for all cases where n equals m, and it's going to be 0 for all cases where n is not equal to m. So what does that do to our double sum? Well, essentially, it means that most of the terms in our double sum are going to be 0. Only the terms where n equals m are going to have value. And so essentially we end up removing one of the indices. Okay, and so in other words, we can think of our Kronecker delta as being this this sort of magical creature that turns a double sum into a single sum, right? If I'm speaking loosely here. So then we end up with a single sum we'll say over n of an, little an, cn star cn, and that's it. And what we were starting out trying to find was our expectation value for operator A in the state phi, and we've derived that expression. So a lot of our problems are going to be maybe not proofs, but they'll be derivations, and we'll have chances to use things like Kronecker deltas and expand, and then simplify, collect terms, figure out which terms are zero, and then you end up with hopefully a simpler expression like we did in this case. So we have derived this or proven that expression and QED. So now we've got another tool in our toolbox. We have our third way of calculating expectation values. This does leave open the problem of determining what are the linear coefficients. And these linear coefficients can be given by how do we find or calculate these individual linear coefficients? All right, so we've sort of left out that part of the problem, and there's a couple of things. Let's see. So let's see if we can find an expression for that. And let me also talk a little bit more about these linear coefficients. Because the linear coefficients are, one way you can think about this, because these linear coefficients are associated with the probability that a system would be found in state at 1 or 2 or n, psi 1, psi 2, psi n, whatever, then there has to be conservation of probability. So there's something that we might want to take note of, which is that because of the relationship to probability, and probabilities, individual discrete probabilities have to add up to 1, then the linear coefficient times its complex conjugate, the sum over those, has to be equal to 1. We can think of this, I'm not really proving it, but we can think of this being related to conservation of probability. All the probabilities have to add up to 1. All the discrete probabilities have to add up to 1. Okay, so we can use that to help prove, but I think I'm actually going to skip the proof. Maybe I'll put it in another video. But it turns out that our individual linear coefficients, it can be shown fairly easily that they're given by an integral over all space. One way to get them. There may be other mathematical approaches where we can skip the integral, but one sort of surefire way, if you actually have a functional form for phi, then it's going to be the individual linear coefficients are given by this integral, psi n star phi. So this is, in fact, this kind of integral shows up. This you can think of as the overlap between these two functions. So this is a type of an overlap integral although the concept of overlap integral is somewhat fuzzier and more broad than how I'm defining it here. But and there are similar integrals that show up in say doing a Fourier expansion. There's also integrals that look like this. And so this overlap integral is basically a measure of how closely psi sub n matches our wave function of interest phi. How much of to what degree does phi have psi sub n character? And it's some complex number, the mod square of which tells us the sort of probability or the some goodness of fit between 0 and 1. Okay, and again, I think I may want to go back and prove that, but I feel like we've done enough of a proof. And that brings us to the end of this lecture. And the next lecture will be on commutation of operators.